Welcome to Year 8 in the Competence-Based Middle Years Program Level 3. This is Sciences, and today we're going to study lesson number 5. We are in unit number 1, and the content of this lesson is going to be first to do a problem on water jet's motion or parabolic motion. Then we will study the linear independence of variables to proceed to analyze the components of a speed, and then a brief introduction to properties of angles called trigonometric functions. So let's first start solving. We know that the maximum height reached by water jet is symbolized by capital H, and it equals the square of the initial speed times the square of the sine of alpha, the initial angle, divided by 2 times the value of gravity. H equals V0 squared times sine squared of alpha divided by twice G. And its maximum distance, symbolized by capital R, equals the square of the initial speed times the sine of twice the initial angle divided by G. R equals V0 squared times the sine of 2 alpha divided by G. Then find the value of H and R if a jet has an initial speed of 3 meters per second and it starts at 30 degrees above the horizontal. We are given the values of the sine of 30 degrees, which is 0.5, and the sine of 60 degrees, twice 30, which is 0.866. Therefore, let's start with the formula of the height. As said, V0 squared times sine squared of alpha divided by 2g. We replace the values. V0 squared is 3 squared. The sine of 30 is 0.5, so the sine squared is 0.5 squared divided by twice 9.8, which is the value of gravity. And now we proceed with that calculation. 3 squared is 9, 0.5 times 0.5 is 0.25, and twice 9.8 is 19.6. When we solve that calculation, we find that the maximum height is 0.11 meters or 11 centimeters. Let's now proceed to the value of R, of the reach. R equals V0 squared times the sine of twice the angle, the initial angle, divided by the value of gravity. We replace the values, so V0 squared is 3 squared. The sine of twice the angle, the sine of twice 30 degrees, sine of 60 degrees is 0.866, and everything divided by 9.8. When we solve that calculation, we obtain 9 times 0.866 divided by 9.8, and that equals 0.8 meters, meaning the jet reaches 0.8 meters forward, and it has a maximum height of 0.11 meters. Let's now analyze what we call the linear independence of variables. Imagine we are at a position given by 2 coordinates, x and y. Or we could say that we call an axis oranges and an axis pears, because we don't really mind what the name is of each of our axes. So let's see an image. Let's represent it with an orange and a pear. Now, if we move along the oranges axis, meaning we increase the value along that axis, we put more oranges, but we don't change the number of pears. Instead of being at point xy, or x oranges plus y pears, we will have more oranges. But as we know, oranges and pears are different, so we cannot add them. The result is having many oranges and still one just pear. With adding none, we still have the same number we had. Now, let's imagine we jump. We have moved first along an axis, then along another axis, and now we jump and we are moving along the vertical axis. We are jumping Z apples because we can imagine we call the vertical axis apples. So we are at x plus delta x. We are at y, and now we are at z because we have jumped. That it means that we will now have the number of oranges we got through adding oranges. We will still have one pear, and now we have one apple. We still have one pear, and now we are adding one apple, which does not change neither the number of pears nor the number of oranges. Same happens when we move along two axes, like we can see in the picture. One, we can move along x, we can move along y, but each of them does not change the value of the other. Or we can have also linearly independent, like oranges and pears, three axes, x, y, and z, in which case we normally call z the vertical axis. So that would be like oranges and pears and apples as well. We have an example with Newton's law of universal gravitation. It's said that he thought of that when sitting beneath an apple tree and an apple fell upon his head. Of course, the story is not necessarily true, but it makes the point very clearly. The apple was on the vertical line above Newton's head, and it moved downwards, pulled by gravity, which pulls towards the center of the earth. And it did not move neither right nor left. It only moved downwards, because downwards is the acceleration of gravity. Now, let's take that concept and imagine the initial speed of a water jet. In the image, we have a representation of the initial speed of a water jet that we are producing. That's the red arrow, and that's the velocity, how the water jet starts its motion. We call that V with the small arrow on top of the letter. That small arrow is extremely important because it indicates that that physical quantity has an orientation, has a direction and a sense, which is shown by the arrow. If we forget the small arrow, is as if we forgot the head of a person. We would be beheading a person. It would not be a person any longer, it would be a corpse, something different. So if we remove the small arrow on top of the letter, we are removing the orientation, we are removing the direction and the sense, and it is something different. So please do not behead those physical quantities who have an orientation, because you would kill them, and we don't want to do that. So now let's draw a vertical dotted line from the end of the arrow until the x-axis. The green segment that we have between the beginning of the arrow and the projection of the end is the projection of the arrow, the projection of the length upon the horizontal axis, and we call that Vx, or component x of the velocity. We now draw a horizontal line from the end of the arrow until the axis Y, and the green segment we have from the origin of the arrow until the projection of the end is the projection of the length of the arrow upon the y-axis, and we call that Vy, or component y of the velocity, Vy. Therefore, components of a physical quantity that has an orientation are the projections of that arrow representing the physical quantity on both axes, or on the three axes if we are working in a tri-dimensional system. We have that angle alpha. We call sine of alpha, sine of angle alpha, the quotient between the opposite side of the triangle we have drawn, Vy, divided by the length of the arrow divided by the hypotenuse. Sine of alpha is the opposite side divided by the hypotenuse. We call cosine of alpha, of angle alpha, the quotient between the contiguous side to the angle Vx and the length of the hypotenuse. V cosine of alpha equals the contiguous side divided by the hypotenuse. Therefore, if we want to calculate the value of Vx, of component x, it equals V times the cosine of alpha, because cosine of alpha equals Vx divided by V. Therefore, Vx equals V times cosine of alpha. And if we want to calculate the value of the opposite, the vertical component, the opposite side to the angle, it is Vy equals V times the sine of alpha, because we have defined the sine as Vy divided by V. A third property of an angle is the tangent. The tangent equals the opposite side to the angle divided by the contiguous side of the angle, Vy divided by Vx. Now, if you take those two values, the numerator and the denominator, and we divide both by the same number, therefore not changing the result, we divide Vy by V, the length of the arrow, and we divide Vx by V, the length of the arrow again. In the numerator, we have Vy divided by V, which is the sine of alpha, and in the denominator, we have Vx divided by V, which is the cosine of alpha. Therefore, the tangent of alpha equals the sine divided by the cosine. We know that the tangent to a curve is a straight line which touches the curve on one single point. We have a representation in the image. The tangent gives us the inclination of that straight line. In the example we have in the image, the tangent is horizontal. The projection on the vertical line, on the vertical axis of that line is 0. So the sine is 0. So the tangent is 0, and 0 is the angle that line forms with the horizontal axis, because that line is horizontal. Let's now see what happens when we produce a water jet. Let's see it with an animation. So we have a reference system, or two axes, and we're going to produce a water jet, which more or less will move like that. It will create a parabola. Let's analyze step by step what we have. But before that, let's remember that gravity affects along the vertical axis. Gravity does not affect along the horizontal axis. And we have seen that, same as happens with oranges and pears, if we change the number of oranges, we do not change the number of pears. Therefore, when we apply gravity along the vertical axis, we will change the vertical component of the velocity, but we will not change the horizontal component of the velocity. Let's see what this means in practice. So let's have our reference system where we are going to analyze step by step what happens with the motion of the water jet. We start the water jet with a given orientation above the horizontal axis, and we represent that initial velocity with the red arrow in the image. We will call that V0, obviously, because it is the initial velocity. Remember, with the arrow on top of the letters, otherwise we are beheading it, and that's not nice. Great, so that's our initial velocity. That initial velocity forms an angle above the horizontal axis that we will call alpha. Now we will draw the projection from the end of the arrow upon the horizontal axis with that dotted line, and the segment we have is the horizontal component of V0, of the initial velocity. We will call that obviously V0x, because it is the x component of V0. And given that it is the contiguous side of the triangle we have drawn, it will be equal to the length of the hypotenuse, meaning V0, times the cosine of the angle. So V0x equals V0 times cosine of alpha. Now we draw another dotted line from the end of the arrow upon the vertical axis, the y-axis, and we obtain the y component of the initial velocity. We call that V0y. And remember, we are speaking of the opposite side to the angle, so V0y equals the hypotenuse times the sine of the angle alpha. V0y equals V0 times sine of alpha. Right, so that's the initial velocity of our jet. But as water proceeds and start moving upwards, what happens? It happens that gravity acts upon water and it starts dragging it downwards. So the trajectory is curved from the origin, and by the moment we reach the point in the image, if we draw the velocity at that moment, it will be tangent to the trajectory. So let's draw the velocity at that point. And because we had called V0 the previous one, we will call this one V1 with the arrow on top. Remember, that is V1. Now, as we said, gravity pulls along the vertical axis and it does not alter the horizontal component. Therefore, when we do the projection of V1 on the horizontal axis, the value we obtain, which will be V1x, it will equal V0x because it does not change. So we can call it directly Vx, which remains constant along the whole movement because the only acceleration we have is gravity, and that operates in the vertical axis. When we now draw the dotted line from the end of the arrow upon the y-axis, we will obtain the vertical component of v1, and we will call that v1y, which is shorter than v0y, because as we go up and gravity pulls down, it is stopping the water jet in the vertical axis. It is reducing it is decelerating the water jet in the vertical axis. We proceed with the movement, and again, as always, gravity keeps pulling down and keeps bending the trajectory. By the time we reach the top, the velocity at the very top is tangent to the curve and therefore is horizontal. The projection, we will call that V2. Again, V2 with a small arrow, never forget the arrow. When we project V2 on the horizontal axis, as it is horizontal, the length of the projection equals the length of the arrow because they are parallel. So V2x equals V0x equals Vx, which does not change. And because it is horizontal, V2y equals 0, because it has no value on the vertical axis. So that's V2. We have reached the top of the motion of the parabola, and then we start moving downwards because we are still being dragged downwards by gravity. Let's see what happens. The water jet proceeds, and we reach the same height as we chose to draw V1. Now we will draw the corresponding velocity at this point, which we will call V3, V0, V1, V2, V3 now. And we are at the same height as we said, and we draw the tangent at that point. V3 with the arrow on top, don't forget it. When we now draw the projections on the horizontal axis, again, we have no change because Vx is not affected by anything. So V3x equals V0x equals Vx. It does not change. And when we draw the dotted line parallel to the x-axis upon the y-axis, we obtain the value of the vertical component, V4y. And V4y, if we look carefully, has the same length as V1y, but it has the opposite value. Now it will be negative. We are moving downwards, and if we have chosen downwards as negative, V4y will have a negative value, and in any case it will be opposed to V1y. We keep moving and we end at the same height as we started. When we draw velocity at that point, it will be tangent to the trajectory, and we clearly see that V4 has the same horizontal component as we have had through the entire process because it does not change. V4x equals V0x equals Vx, and the vertical component has the same value as it had at the beginning, but again with the opposite sign. So V4y equals minus V0y. Let us now, to end this lesson, analyze the values of the main trigonometric functions of some very characteristic angles. To do that, we use a very special circumference, a circumference that we call goniometric circumference. That's a very nice name. It comes from the Greek, as so many times, because in Greek, gonia means angle. So the goniometric circumference is a circumference that we use to measure things with the angles. And the characteristic of this circumference is that its radius equals 1, and therefore the hypotenuse of the triangles that we will draw will always be 1. Remember, the sine of an angle equals the opposite side divided by the hypotenuse. In this case, as the hypotenuse is going to be 1, the sine of alpha will equal the opposite side to the angle because it is divided by 1. And the cosine, again divided by the hypotenuse, which is 1, will equal the contiguous side to the angle. So let's now analyze the most characteristic values of angles, as we were saying. What happens when alpha equals 0? When alpha equals 0, the horizontal projection equals the radius, which is 1. Therefore, the cosine of 0 is 1 divided by 1 equals 1. And the sine of alpha, the projection on the vertical axis, is a point, is a dot, it is 0. Therefore, it is 0 divided by 1. So the sine equals 0. When we have 30 degrees, we see in the image that the projection on the vertical axis is half the radius. Therefore, the sine of 30 degrees is 0.5 divided by 1, and that is 0.5. The sine of 30 degrees equals 0.5. Now, the contiguous side, if we apply Pythagoras' theorem, we will see it is square root of 3 divided by 2, and that is 0.866. So the sine of 30 is 0.5, the cosine of 30 is square root of 3 divided by 2 equal 0.866. Again, if we do 45 degrees, we will see that in both cases, the value is the same. Therefore, when we calculate the square root of 2 divided by 2 is the length of the contiguous side and also the opposite side, which is 0.707. Those are the sine and the cosine of 45 degrees. When you have 60 degrees, we are in the opposite situation as we were with 30 degrees. The horizontal projection is half the radius, therefore the cosine of 60 is 0.5, and the vertical projection is square root of 3 divided by 2, equaling 0.866. And when we reach 90 degrees, the horizontal projection is 0 and the vertical projection is 1. Therefore, the sine of 90 degrees is 1 and the cosine of 90 degrees is 0. I hope you have enjoyed this introduction to the linear independence of variables, to how to analyze a parabolic motion, and to the main trigonometric functions. In science, as always, enjoy. As an extension, and to learn how to calculate the values of the sines and the cosines, let's take the case of the 30-degree angle. Remember, the value of radius is 1. So first of all, let's get a larger image of a straight triangle with a 30-degree angle. We will call the hypotenuse A, we will call B the contiguous side, and we will call C the opposite side. Applying Pythagoras' theorem, we know that the square of the hypotenuse equals the addition, the sum of the squares of the two sides. But we know that the hypotenuse is 1, and we also see in the image that the value of C is 0.5, half the radius, which is 1. Therefore, we can write that 1 squared equals B squared plus 0.5 squared. If we subtract 0.5 squared on both sides, we will obtain that 1 squared minus 0.5 squared equals B squared. But 0.5 squared is 0.5 times 0.5, that's 0.25. So we can write that 1 minus 0.25 equals B squared. Therefore, B squared equals 0.75, which is 3/4. Now, this is B squared. We need to calculate the square root of both sides. So B, which is the square root of B squared, equals the square root of the 3/4, which is square root of 3 divided by square root of 4, which is square root of 3 divided by 2. And square root of 3 is 1.732. So we have 1.732 divided by 2, and that is 0.866. Therefore, as we were saying, the sine of 30 degrees is 0.5, and the cosine of 30 degrees is 0.866. We use the same procedure to calculate the values of the trigonometric functions of all the angles. In science, as always, enjoy.